Understanding the join order in SQL. Many SQL beginners assume that the order of tables in a join operation does not affect the query's result. However, this is not always true. The sequence in which tables are joined can significantly impact the output, especially when using different types of joins or complex queries. The order of tables in a join can influence both the result set and the performance of a query. SQL engines process join operations in the order they are written in the query, unless the query optimizer intervenes. Each join produces an intermediate result set, which serves as the input for the next join. The type of join used, such as inner join, left or right join, or full join, determines which rows are included or excluded in this intermediate result. If the join order changes, the intermediate result sets may differ, potentially altering the final output. The number of rows returned by a query can change depending on the join order, particularly when mixing different join types. For example, an inner join only includes rows where there is a match in both tables. A left join retains all rows from the left table, even if there is no match in the right table, potentially increasing the row count. A right join does the opposite, keeping all rows from the right table. If a left join is followed by an inner join, rows from the left table that survived the left join might be filtered out by the inner join if they do not match the next table. Changing the order of these joins could preserve or eliminate different rows. Modern SQL databases use a query optimizer to determine the most efficient way to execute a query. In some cases, the optimizer may reorder joins internally to improve performance, regardless of the order specified in the query. However, this behavior is not guaranteed, especially with complex queries or certain join types. Explicitly writing joins in a logical order can help ensure predictable results and improve readability. The join order can also affect query performance. Joining smaller tables first or reducing the size of intermediate result sets early in the query can lead to faster execution. For example, applying an inner join to filter rows before a left join might reduce the number of rows processed in subsequent joins. Poor join ordering can lead to large intermediate result sets, slowing down the query. Best practices for managing join order. Understand your data, know the relationships between tables, like one-to-many, many-to-many, and how join types affect row inclusion. Test query results. When combining different join types, test the query with sample data to verify the output matches your expectations. In complex queries, use parentheses to group joins explicitly, making the order of operations clear. Place restrictive joins, like inner join with selective conditions, earlier in the query to reduce the size of intermediate result sets. Use filtering in the join operation to minimize the rows returned. Leverage explain or explain query plan, or analyze, or set show plan _all on. While these techniques are not typically for beginners, diving into query planners is highly recommended as you gain more experience with SQL. Use your database's query planner to understand how the engine processes your joins and whether the optimizer is reordering them. Conclusion. The order of tables in a join operation can significantly affect both the result set and the performance of a SQL query. While the query optimizer may mitigate some issues, relying on it entirely can lead to unexpected outcomes, especially in complex queries. By carefully planning the join order, testing results, and following best practices, you can ensure your queries produce the desired output efficiently. This slide presents our names, ages, and hair_color tables along with the data they contain. As you can see, the names table contains 3 records, the ages table also has 3 records, and the hair_color table has 4 records. Due to the use of inner joins in both of our queries, only records with matching entries across all referenced tables will appear in the final result set. This means that not all records from the names table will be included in the output, as only those records with corresponding entries in both the ages and hair_color tables will be retained. For example, if a name in the names table lacks a matching record in either the ages or hair_color table, it will be excluded from the query results. This behavior highlights the importance of understanding how inner joins function when combining data from multiple tables, ensuring that only fully matched records are returned. This is a small dataset for demonstration, but in real-world scenarios, tables often contain thousands or millions of records. While you do not need to know every specific entry in your tables, you must understand the type of data each table holds, such as names, numbers, or categories, to create effective and accurate queries. Without this knowledge, building working queries becomes nearly impossible, as data types dictate how tables can be joined and filtered. Impact of swapping left join and inner join in SQL. The order of join operations in a SQL query can significantly affect the result set, especially when combining different join types like left join and inner join. To illustrate this, let us analyze an example query, swap the join types, and compare the results step by step. Consider our three tables: names, hair_color, and ages. Let us focus on 1 Alice, 2 Bob, and 3 Carol. We start with the following query. Select n.id, n.name, h.color, a.age. From names as n. Left join hair_color as h on n.id equals h.id. Inner join ages as a on h.id equals a.id. The result set is ID, name, color, age. 1. Alice, blonde, 25. Step by step. The left join between names and hair_color keeps all rows from the names table and includes matching rows from hair_color. If there is no match, null is returned for the hair_color table's columns. The intermediate result contains Alice, Bob, and Carol. The subsequent inner join with ages only keeps rows where there is a match between the intermediate result and the ages table. The final result contains Alice. Now, let us swap the join types and analyze the following query. Select n.id, n.name, h.color, a.age. From names as n. Inner join ages as a on n.id equals a.id. Left join hair_color as h on a.id equals h.id. Result set. ID, name, color, age. 1. Alice, blonde, 25. 2. Bob, null, 30. Step-by-step execution. The inner join first filters the result to include only names with matching ages. The intermediate result contains Alice and Bob. The left join with hair_color keeps all rows from the intermediate result and includes matching rows from hair_color. If there is no match, null is returned for hair_color columns. The final result contains Alice and Bob. Swapping the left join and inner join changes the result set significantly. In the original query, left join then inner join, the left join includes all names, but the inner join filters out rows without a matching age. In the swapped query, inner join then left join, the inner join first limits the result to names with matching ages, and the left join includes all of these rows. This example demonstrates that the order and type of join operations matter. The inner join is restrictive, filtering out non-matching rows, while the left join is inclusive, preserving rows from the left table. Understanding these mechanics is crucial for writing predictable SQL queries. This slide displays the results for two queries, demonstrating how join order affects the output. Query 1, we start with the left join, followed by an inner join. Left join hair_color as h on n.id equals h.id. Inner join ages as a on h.id equals a.id. Result, 1 row, Alice. The left join includes all names, but the inner join filters to only rows with matching ages.id. Query 2, now we start with the inner join, followed by the left join. Inner join ages as a on n.id equals a.id. Left join hair_color as h on a.id equals h.id. Result, 2 rows, Alice and Bob. The inner join limits to names with matching ages, then the left join keeps all these rows. SQL processes joins sequentially, with each join's result feeding into the next. Left join first, keeps all rows from the left table, a following inner join may filter them. Inner join first, restricts to matching rows, a following left join preserves those rows. Plan your join order carefully to achieve the desired result set. Understanding self-join. What is a self-join? A self-join occurs when a table is joined with itself, allowing you to compare rows within the same table. This is useful for hierarchical relationships, employees and their managers. Referential relationships, customers who referred others. Row comparisons, pairing people based on shared attributes. Our case, finding pairs of people who live in the same city. To explore a self-join, let us first expand our names table by adding 3 new people, David, Eve, and Frank. The table includes a city column to store their locations. Insert into names, ID, name, city. Values. 4, David, New York. 5, Eve, Chicago. 6, Frank, Los Angeles. Self-joins. Performance considerations. Self-joins can impact performance, especially on large tables, due to their potential for a Cartesian effect. Without proper filtering, a self-join compares every row with every other row. For a table with 1,000 rows, this could lead to 1,000 times 1,000 equals 1,000,000 comparisons, significantly slowing down the query. In real-world databases, tables often have millions of rows, making this issue critical. Best practices to mitigate. Use conditions, add where clauses or specific on conditions to limit comparisons, as n1.id less than n2.id. Index columns, create indexes on columns used in the join, like city, to speed up lookups. Test with small data, verify the query's behavior on a small dataset before running it on large tables. Monitor performance, analyze the query plan and identify bottlenecks. Self-joins are powerful for uncovering relationships within a table, but they require careful design. As we will see in the next slide, our updated names table reveals city-based pairings, highlighting the self-joins utility. The updated names table. This slide shows the result of adding David, Eve, and Frank to the names table, along with the full table content. Insert statement. Insert into names, ID, name, city. Values. 4, David, New York. 5, Eve, Chicago. 6, Frank, Los Angeles. View the content. Select asterisk from names. Resulting table. ID, name, city. 1, Alice, New York. 2, Bob, Los Angeles. 3, Carol, Chicago. 4, David, New York. 5, Eve, Chicago. 6, Frank, Los Angeles. The updated names table now contains 6 rows, with 3 distinct cities. New York, Alice and David. Los Angeles, Bob and Frank. Chicago, Carol and Eve. This city distribution sets the stage for our self-join, which pairs people living in the same city. Self-join to find city-based pairs. Let us say we want to find pairs of people who live in the same city. Select n1.name as person 1, n2.name as person 2, n1.city. From names as n1. Join names as n2. On n1.city equals n2.city and n1.id not equal to n2.id. How it works. Self-join, the names table is joined to itself, with aliases n1, first person, and n2, second person. Join condition, n1.city equals n2.city matches rows where both people live in the same city. Avoid self-matches, n1.id not equal to n2.id prevents a person from being paired with themselves, as Alice with Alice. Selected columns, n1.name, person1, n2.name, person2, and n1.city, shared city. As you see, we join the names table as n1 to the names table as n2. The output: person1 person2 city. Alice David New York. David Alice New York. Bob Frank Los Angeles. Frank Bob Los Angeles. Carol Eve Chicago. Eve Carol Chicago. Issue: duplicate pairs. The output shows each pair twice, like Alice David and David Alice, which is redundant. This happens because the self-join considers both directions of the pair, n1 as Alice, n2 as David, and vice versa, and n1.id not equal to n2.id only prevents self-matches, not duplicates. Fixing duplicate pairs in our self-join. In the previous slide, our self-join query produced duplicate pairs, Alice David and David Alice. Let us fix this to show only unique pairs of people who live in the same city, making the output cleaner and more efficient. Select n1.name as person1, n2.name as person2, n1.city. From names as n1. Inner join names as n2. On n1.city equals n2.city and n1.id less than n2.id. What changed? Original condition, n1.id not equal to n2.id prevented self-matches, as Alice with Alice, but allowed both directions of each pair, as Alice David and David Alice. New condition, replaced n1.id not equal to n2.id with n1.id less than n2.id, ensuring each pair appears only once by requiring person1 to have a lower id than person2. Join type, specified inner join for clarity, as we only want pairs with matching cities. Self-join, the names table is joined to itself, with aliases n1, first person, and n2, second person. Join conditions, n1.city equals n2.city, matches people who live in the same city. n1.id less than n2.id, this ensures unique pairs by ordering the pair based on id, only Alice David, not David Alice. Output: person1 person2 city. Alice David New York. Bob Frank Los Angeles. Carol Eve Chicago. Benefits of the fix: cleaner output, shows only unique pairs, making the result easier to read and interpret. Improved efficiency, reduces the number of rows processed and returned. Without n1.id less than n2.id, the join evaluates both directions of each pair, like 6 rows for 3 pairs. With n1.id less than n2.id, only one direction is considered, having the output size for paired data. Scalability, for larger tables, like 1000 rows, avoiding duplicates prevents exponential growth in result size, improving performance. Use precise conditions. n1.id less than n2.id is a common technique in self-joins to ensure unique pairs, applicable to any column that imposes a consistent order. Index join columns. An index on city can speed up the n1.city equals n2.city comparison, especially for large tables. Test incrementally, run the query on a small dataset, like our 6-row table, to validate results before applying to larger datasets. Comparing self-join conditions. This screenshot shows the results of our self-join on the names table to pair people by city, using different ID conditions. A self-join compares every row in the table to every other row, including itself, unless we specify conditions to control the matches. Let us explore how each condition affects the output. The base self-join query is: select n1.name as person1, n2.name as person2, n1.city. From names as n1. Inner join names as n2 on n1.city equals n2.city. If we add a condition, and n1.id equals n2.id, every person would only match with themselves. The partial result will be Alice Alice New York. Matches self only, n1.id equals n2.id forces each row to match with itself, as the ID must be identical. Each person in a city pairs with themselves, as Alice Alice, David David for New York. This produces one row per person in the table. We add the condition, and n1.id not equal to n2.id, this prevents self-matches, n1.id not equal to n2.id excludes self-pairs, like Alice Alice, allowing only different people in the same city to match. Duplicate pairs, for each city pair, both directions appear, as Alice David and David Alice, doubling the output. The partial result is displayed on your screen. Alice David New York. David Alice New York. We add the condition, and n1.id less than n2.id. Now we get unique pairs. It ensures each pair appears once by requiring person 1 to have a lower ID than person 2, as Alice, ID equals 1, before David, ID equals 4, and not vice versa. Result, produces one row per unique pair, like one row for New York. Eliminates duplicates, making the output concise and efficient, ideal for most pairing scenarios. The partial result is displayed on your screen. Alice David New York. If we leave the condition out, the partial output will be Alice, Alice New York. Alice, David New York. David, Alice New York. David, David New York. Without an ID condition, every row in a city matches every row, including itself and both directions of pairs. Result, for New York, 2 people, we get 2 times 2 equals 4 rows, Alice Alice, Alice David, David Alice, David David. Expanding the names table for our self-join. To make our self-join example more interesting, we add 2 new people to the names table, Grace in Boston, a new city with 1 person, and Henry in New York, increasing New York's residents. Adding new data with the insert statement. Insert into names, ID, name, city. Values. 7, Grace, Boston. 8, Henry, New York. Grace, ID equals 7, the first person in Boston, a new city with only 1 resident. Henry, ID equals 8, the third person in New York, joining Alice and David. The names table now has 8 rows, with New York having 3 people, Boston 1, and Los Angeles and Chicago 2 each. City distribution. New York, Alice, David, Henry. Los Angeles, Bob, Frank. Chicago, Carol, Eve. Boston, Grace. Let us rerun our optimized self-join query to find unique pairs of people living in the same city, using the updated names table with 8 rows, including Grace in Boston and Henry in New York. We analyze the output, understand why Boston is missing, and discuss the self-join's effectiveness on small versus large data sets. Select n1.name as person 1, n2.name as person 2, n1.city. From names as n1. Inner join names as n2. On n1.city equals n2.city and n1.id less than n2.id. Person 1, person 2, city. Alice, David New York. Alice, Henry New York. David, Henry New York. City breakdown. New York, 3 people, Alice ID equals 1, David ID equals 4, Henry ID equals 8. Why Boston is missing, the self-join requires at least 2 people per city to produce a pair. Since Grace is alone in Boston, no matches are generated for that city. Our names table has only 8 rows, which limits the self-join's complexity and impact. The small size does not fully showcase the self-join's power for complex relationships like hierarchies or large-scale comparisons. For small data sets, simpler methods like group by or manual inspection might suffice. Large data sets, self-joins shine when comparing thousands or millions of rows, such as finding employee-manager hierarchies in an organization, identifying customers who referred others in a large database, pairing products with similar attributes in an e-commerce catalog. Without proper conditions, comparisons grow quadratically, like from a 1,000 rows to a 1 million comparisons, slowing queries. In a table with 1,000 people across 50 cities, a self-join could generate thousands of pairs, revealing patterns, as cities with high resident overlap, that group by alone cannot capture. Alternative to the self-join with group by. In previous slides, we used a self-join to find pairs of people living in the same city. Here, we explore a simpler alternative using group by, having, and string_ag to list cities with multiple residents and their names in a single row. This approach is more concise for summarizing city populations, especially for our small names table. Group by query. Select city, string_ag, name, as residents. From names. Group by city. Having count, asterisk, greater than 1. Group by city, groups all rows by unique city values, collapsing rows with the same city into a single row. String_ag, name, concatenates the name values for each city into a comma-separated string, as Alice, David, Henry for New York. Having count, asterisk, greater than 1, filters the results to include only cities with 2 or more residents, excluding cities like Boston with only 1 person. Output. City, residents. New York, Alice, David, Henry. Chicago, Carol, Eve. Los Angeles, Bob, Frank. Why Boston is missing, the having clause filters out cities with fewer than 2 residents, so Boston, with only Grace, does not appear. Null values. Let us talk a little about null values. Null values in SQL often confuse beginners and trip up even seasoned developers, as I discovered when transitioning from IT to databases. Their mysterious behavior demanded careful handling. This section demystifies nulls with practical examples on how to handle them. Refer to the slide for examples. In databases, conditions involving null, such as column equals null or column not equal to null, evaluate to unknown rather than true or false, adhering to the SQL standard's 3-valued logic. This is crucial because null represents an unknown value. Treating it as unknown ensures logical accuracy in query results. This prevents incorrect assumptions that could exclude rows unexpectedly, like where column not equal to 5 excludes null rows. It impacts query optimization, as the optimizer accounts for unknown in execution plans, potentially avoiding indexes for null comparisons unless null is used. This behavior enhances correctness in complex queries, joins, and aggregates but requires explicit null handling, as is null. MySQL also follows the 3-valued logic, but introduces a non-standard null-safe equality operator or null-safe comparison operator for null-safe comparisons, simplifying some queries. See the slide for the symbol. Most databases require null for null checks, ensuring portability but demanding explicit logic. The MySQL own operator allows direct null comparisons. This is convenient, but non-portable and may lead to less predictable optimizer behavior in complex queries due to MySQL's simpler optimizer. Let us talk about ignoring how nulls behave in where clauses. Imagine you are querying a table of customers to find those with a specific status, like where status equals inactive. Seems straightforward, right? But what if some rows have status null? In SQL, null is not equal to anything, not even itself. So, status equals inactive skips rows where status is null, which might exclude customers you meant to include. For example, if you are counting inactive customers, you might undercount because nulls are silently ignored. The fix? Always check for null explicitly with null or not null. So, you can write where status equals inactive or status is null to catch those cases. This is critical in databases where null handling is strict. Ignoring nulls can lead to wrong results, so always think, does my query handle nulls correctly? It is a small check that saves big headaches. That's a wrap for this lesson. You have mastered the join order and the self-join, great work. In our next video, we will dive into concat, transforming text, and the cross-join to complete your join toolkit. Keep practicing to solidify your skills, and I see you in the next lesson.